So today we are considering C0 semigroups. So a semigroup of linear operators for non-negative t's. It's a semigroup of class C0 if for each x we have that S of t of x goes to x as t goes to 0 with positive values. So the difference with uniformly continuous semigroups is that for uniformly continuous semigroups, ST converges to identity in the operator norm. Here, it's for each fixed x, meaning that this convergence is on the Banach space capital X. All right, so the following theorem holds. So when you have a semigroup, a C0 semigroup, then you can find a constant m, non-negative, and omega, a number omega such that for all t, the norm of st, so here again, it's the operator norm, is less than a constant m, the constant m, times exponential of omega t. And so we are going to prove that. So the first step in the proof of the theorem is, so we claim that there's a typo here. There's exist a m greater than 1 and a mu, a positive mu, such that the norm, again in the operator norm of st is less than m in at least a small interval 0 mu. We claim that that's true. So so to prove that this is true, we are going to assume that's not the case, and this will lead to contradiction. Oops. So assume that we cannot find such a m and mu. Then, if by saying that if that's not true, for each m so it's greater than 1. It's not it's a strict inequality here. And for all mu positive, I can find a t. It depends. This t depends on the m and the mu in 0 mu, such that the norm of such s of t is greater than m. So I can choose whatever m I want and whatever mu I want. So I choose m equals n and mu equals 1 divided by n. So I obtain that. But we have to remind that ST is a C0 semigroup. So in fact, for each X, STN converges to STN of X converges to X. So if this is true, then for fixed X, I have the supremum here of STN of X is finite because it converges. But then I can apply the uniform boundedness theorem. I refer you to any classic book of functional analysis to find the theorem. And explicitly in this case, from this assumption or from this fact, I can conclude that, in fact, I have that the sup over the n of the norm of STN, the operator norm is finite. So this is the conclusion of the uniform boundedness theorem. But that's a contradiction. That's a contradiction with the negation at the beginning. So finally, we have such a m greater than 1 and such a mu. So now we need to consider any positive t, and we need to express it as mu, because that's there that I have the estimation. So writing t as n mu plus delta, where n is an integer and delta is smaller than mu, a positive number smaller than mu, from the property of the semigroup, I deduce that this holds, and therefore this holds, and finally, let me do something like that. By applying this those computations, I obtain this result, which proves the theorem. So a few definitions. So a C0 semigroup is called a C0 semigroup of type M omega if ST of L of X is less than M exponential the omega T. And in the case where I have this bound by 1, I call it a C0 semigroup of contractions. All right, so the idea to define this integral is to look at this sum. And t divided by n. And this is the natural extension of the Riemann integral to the operator, to the integral of this operator. So is it reasonable to do that? Yeah, we can prove actually that the left side will converge to something, and we call it the integral. So to prove that it converges, what we are going to do is to prove that if I call that one, let's say Tn, this Tn is a Cauchy sequence in L of x. So Tn is a Cauchy sequence in. So we need to look at Tn minus Tp. So we will assume n greater than p. And so I write just the sum. It's like that. And so our goal is to prove that the norm of this thing as an operator is as small as I want if n and p are large enough. So in order to compare these things, we are going to draw our interval 0t. And so first, so you divide this interval by p. Let's do it in blue. And so this is t divided by p. And then you will divide it by n. So let's do it by n. So what I'm going to do, I'm going to consider all the red and blue. And so in yellow, I take it all of these. So sorry. Okay, and I just call them. So T node, T1, T2, T3, etc. So doing that, I can rewrite my sum as Tn minus Tp equals sum of, let's say, sum over I, and here I will get, so for example, so the n here, I will write it like that. Phi, but I call it phi n because it's related to the first to the n, to tn. So s phi n of I and here it's ti plus 1 minus ti minus the sum also over I and s of phi p I and the same sum. You know, for example, so here at T1, for example, S phi n of 1 is 1 divided by n. So for example, so phi n of 1 is 1 divided by n. But phi p of 1 here is just 0. Right? Because my p changes at 1 divided by p. So by doing that, what I get, so I can write it now. So I can write Tn minus Tp equals sum over I. And now I have Ti plus 1 minus Ti. And I can write it as S phi and I minus S phi p of I. And the thing is, when I do these things, I'm always, the thing is that by construction, my phi n of I and phi p of I are always at a distance which is less than 1 over p. Yeah, because they by construction. So let's do it again. So let's do it again here. So for example, my as I said here, I can put in blue, phi n of 1 is 1 divided by n, and phi p of 1 is 0, because here when I'm here, yeah, so you can see that yeah, so these two numbers will also be at a distance less than 1 divided by p. All right, so that what's the conclusion of that? So now if I look at the norm, if I look at Tn minus Tp is less than sum over I, the norm here, and Ti plus 1 minus Ti. And since the semigroup is uniformly continuous, I can write that S phi n phi minus S phi p I in norm you have that, but because it's uniformly continuous, there exists, let's call it nu, such that if the norm like S2 minus S1 is less than nu, then the norm of S2 minus S1 is less than epsilon. This is true because the operator is uniformly continuous, and because you can always write it. So assume that S2 is greater than S1, you can write it like that. So this comes from the fact that my operator is my ST is uniformly continuous. So if this is small enough, then the distance between the two is small enough. Now I can if my P is large enough, I can put it this one less than epsilon. So when I make the sum, I will get that. In fact, this sum, it follows that. It follows that Tn minus Tp is less than epsilon, the sum over E of and did I forget something? Yeah. All right, I could add a constant, but that's true too. So yeah, so I can always do that, and this is nothing but T. This pass by construction is T. So that's it. So Gn is Cauchy, and therefore it converges. So when we talk oh, I'm too far. Yeah. So when we talk about this thing, if S is uniformly continuous, I'm talking about this limit that I just constructed. So it's well defined. It has all the properties that you can imagine for the integral. And if S of t is not uniformly continuous, but only a C0 semigroup, the same thing holds, but for each x, for each given x in the space capital X. And you can do exactly the same. And so there's a generalization from the Lebesgue integral to the to semigroups, or even more general when you work in Banach spaces, and this is called the Bochner integral. So you can have a look at you can look it in the internet, or it's done in in the book of Yoshida Functional Analysis, chapter 5, section 5. You can have also more modern views. Yeah, so it's an exercise to have a look at these Buchner integrals. From now on, if I don't, we can right now we can deal with just the Riemann integral is fine for what we are doing now. So we will see a lot of integrals, and this is well defined for operators. That's the point.